Far beyond the boundaries of Earth's atmosphere lies a realm of invisible but powerful forces that shape our planet's environment in ways many rarely consider. This realm, governed by the sun's dynamic energy and magnetic fury, is known as space weather. Unlike terrestrial weather, with its familiar winds, rain, and storms, space weather is driven by streams of charged particles and magnetic fields erupting from the sun, traveling across the vacuum of space to interact with Earth's protective magnetic bubble. These celestial storms, while distant, hold the potential to disrupt life on Earth in profound ways. At the heart of space weather is our sun, a fiery sphere of plasma undergoing constant magnetic turmoil. Its surface, though seemingly steady from our vantage point, is dotted with sunspots, darkened regions where intense magnetic fields twist and knot. These sunspots serve as epicenters for violent solar activity. When the magnetic tension reaches a critical point, it releases energy explosively in events called solar flares, unleashing bursts of electromagnetic radiation across the spectrum, from radio waves to high-energy X-rays and ultraviolet light. These flares, though brief, can flood space near Earth with radiation capable of interfering with satellites and radio communications. Even more dramatic than flares are coronal mass ejections, or CMEs. These vast clouds of plasma, containing billions of tons of charged particles entwined with magnetic fields, erupt from the sun's corona, the outer atmosphere, at incredible speeds. Unlike the radiation from flares, which travels at light speed, CMEs move more slowly but carry enormous mass and magnetic energy. A CME heading directly toward Earth can take between 1 to 3 days to arrive, offering a crucial window for detection and warning. As a CME approaches, it collides with the solar wind, the constant stream of charged particles flowing outward from the sun, and the combined forces push against Earth's magnetosphere, the magnetic shield generated by currents deep within our planet's molten iron core. This invisible shield extends tens of thousands of kilometers into space, deflecting most solar particles and protecting life from harmful radiation. However, a strong CME can compress this shield, inject charged particles, and induce electrical currents that cascade through the magnetosphere and ionosphere, triggering a geomagnetic storm. The 11-year solar cycle governs the rhythm of these solar activities. Every cycle begins with a solar minimum, a period of relative calm with few sunspots and rare storms, gradually ramping up to a solar maximum when sunspot numbers surge and solar storms become frequent and intense. Scientific models forecast that the solar maximum around 2025 will be active enough to pose a serious threat of large solar storms. This anticipation raises pressing questions about how prepared Earth is for the potential chaos these storms could unleash. Monitoring the sun's behavior involves an intricate web of satellites, observatories, and ground-based instruments. Satellites like NASA's Solar Dynamics Observatory provide continuous high-resolution images of the sun's magnetic fields and eruptive events, allowing scientists to observe sunspots grow, flare, and sometimes erupt with CMEs. Spacecraft positioned between the sun and Earth, such as the Advanced Composition Explorer, measure the solar wind's speed, density, and magnetic orientation in real time, essential data for forecasting geomagnetic storms. Despite decades of research and advances in technology, predicting the exact timing, trajectory, and severity of solar storms remains a scientific challenge. The sun's magnetic environment is chaotic, and even slight changes in a CME's orientation can drastically affect its impact on Earth's magnetosphere. A CME with a magnetic field aligned southward relative to Earth's magnetic field will reconnect more efficiently, releasing greater energy into the magnetosphere and triggering more severe geomagnetic storms. The historical record of solar storms reveals the scale of potential disruption. The most powerful recorded event, the Carrington event of 1859, produced auroras visible near the equator and damaged telegraph systems worldwide. Telegraph operators reported shocks and sparks. Some systems caught fire. Although technology was relatively simple then, the event demonstrated that solar storms can severely disrupt human infrastructure. Fast forward to today, and the stakes are exponentially higher. Satellites orbiting Earth govern navigation, communications, weather forecasting, and national security. Power grids light and cool our cities. Aviation relies on uninterrupted communication and GPS navigation. The interconnected web of technology that supports modern life makes society highly vulnerable to space weather disturbances. Looking ahead to 2025, scientists warn that a major solar storm could have devastating consequences if Earth faces a CME as intense as or stronger than the Carrington event. The potential damage could range from satellite malfunctions and communication blackouts to widespread power outages and economic disruption. The sun's tempestuous moods, once merely a curiosity for astronomers, have become a central concern for governments and industries worldwide. Understanding the fundamental nature of solar storms, their origins on the sun, their journey through space, and their interaction with Earth's magnetic shield, is the first step toward appreciating the risks they pose. This cosmic phenomenon is a powerful reminder of our planet's fragile place in the solar system, where unseen storms from a distant star can reach across millions of kilometers to challenge the very fabric of our technological civilization. As 2025 approaches, the story of solar storms is not just one of space science, but of global preparedness, resilience, and the ongoing dialogue between humanity and the star that sustains it. When a massive cloud of solar plasma hurtles toward Earth, it carries with it more than just charged particles. It transports an invisible force capable of shaking the very magnetic cocoon that protects our planet. This force ignites a geomagnetic storm, a tempest in space that unfolds in the magnetosphere, the magnetic bubble surrounding Earth, with consequences that ripple down to the ground. Unlike terrestrial storms of wind and rain, this storm is composed of magnetic fields and high-energy particles colliding with Earth's magnetic environment, triggering a chain reaction that can disrupt technology, power grids, and even the delicate balance of life at high altitudes. At the heart of this storm is the magnetic interaction between the CMEs embedded magnetic field and Earth's own magnetic shield. The magnetosphere is usually a resilient guardian, deflecting charged solar particles harmlessly into space. However, when the CME's magnetic field is oriented southward, opposite Earth's northward field, it opens a magnetic gateway through a process called magnetic reconnection. This process snaps and reconnects magnetic field lines, releasing immense energy and allowing solar particles to flood into the magnetosphere. This sudden influx energizes particles trapped in the Van Allen radiation belts, donut-shaped zones of high-energy electrons and protons encircling the planet. These particles accelerate to near light speed, spiraling along magnetic field lines toward Earth's poles. Upon reaching the upper atmosphere, they collide with atoms and molecules, exciting them and causing the breathtaking auroras that light up polar skies with curtains of green, red, and purple. While the auroras are a beautiful side effect, they are visual markers of intense space weather activity with deeper consequences. The injection of charged particles and the shifting magnetic environment induce electric currents not only in space but also within Earth's crust and oceans. These geomagnetically induced currents, GICs, can flow through conductive infrastructures such as pipelines, railways, and most critically, power grids. Transformers and electrical substations, designed to operate under relatively stable conditions, can become overwhelmed by these abnormal currents, causing overheating, damage, or even permanent failure. The vulnerability of power grids to geomagnetic storms is one of the most alarming aspects of space weather. The 1989 geomagnetic storm, for example, led to a massive blackout in Quebec, Canada, leaving millions in the dark for hours. The damage was largely caused by GICs saturating transformers and tripping protective systems. Today's grids are even more complex and interconnected, meaning a severe solar storm could trigger cascading failures, potentially plunging entire regions or countries into prolonged outages. Beyond terrestrial power infrastructure, satellites orbiting Earth are frontline victims of geomagnetic storms. The high-energy particles accelerated during a storm can penetrate spacecraft shielding and damage sensitive electronics through radiation effects known as single-event upsets, where charged particles alter microelectronic circuits. Solar panels degrade more rapidly under intense particle bombardment, reducing their power generation capacity. Sensors and communication systems may suffer interference or temporary loss, impairing critical functions such as navigation, weather monitoring, and military reconnaissance. Geostationary satellites positioned about 36,000 kilometers above Earth to provide continuous coverage are particularly exposed during storms that compress the magnetosphere closer to Earth. Similarly, low Earth orbit satellites used for Earth observation and the International Space Station face increased radiation risks, potentially endangering astronauts. Space agencies and satellite operators maintain constant vigilance, putting satellites into safe modes during severe solar events to minimize damage. But the risk remains significant. The ionosphere, a charged layer of the upper atmosphere essential for radio wave propagation, undergoes rapid and unpredictable changes during geomagnetic storms. Fluctuations in ionospheric density and composition can degrade or black out high-frequency radio communications, impacting aviation, maritime operations, and emergency services relying on reliable long-distance communication. GPS signals, critical for navigation on land, sea, and air, can also become erratic, undermining precision in timing and location-dependent systems. Even the health of humans beyond the protective layers of Earth's atmosphere can be affected. Astronauts aboard the International Space Station receive increased radiation exposure during geomagnetic storms, necessitating temporary shelter in shielded areas. Airlines reroute high-latitude flights to lower altitudes or different paths to reduce radiation doses for passengers and crew. As human exploration extends toward the Moon and Mars, understanding and mitigating solar storm radiation risks become vital for mission planning and astronaut safety. The cascading effects of geomagnetic storms are not limited to technology. They touch the economy and daily life. Disruptions in satellite-based communication and navigation can halt financial transactions, delay shipments, and interrupt telecommunications. Power outages can incapacitate hospitals, water treatment plants, transportation systems, and supply chains. Emergency services might be overwhelmed by calls for assistance, yet constrained by degraded communications and transportation. Governments and industries have begun to grasp the scale of these threats. Efforts to harden power grids include installing devices that block or divert GICs, reinforcing transformers, and developing rapid response protocols. Satellite designs now incorporate improved radiation shielding and redundancy to withstand storm conditions. Space weather forecasting centers worldwide issue alerts and warnings to help operators prepare and mitigate damage. Despite these advancements, the unpredictability of solar storms and the interconnected nature of global infrastructure mean no system is entirely immune. A severe geomagnetic storm hitting Earth in 2025 during the upcoming solar maximum could stress the world's technological and emergency response capabilities to their limits. The event would test not just scientific understanding and engineering, but also the coordination between governments, industries, and the public. In this dance between cosmic forces and human systems, the threat of geomagnetic storms stands as a humbling reminder of our dependence on technology and the environment beyond our atmosphere. It reveals how the invisible and distant sun, over 150 million kilometers away, can wield power over Earth's delicate electric grid, satellite networks, and communication lifelines. The story of geomagnetic storms is both a saga of natural cosmic dynamics and a modern tale of resilience, preparation, and the ongoing effort to safeguard our way of life in an unpredictable universe. Imagine a world suddenly plunged into darkness, not by a natural disaster like a hurricane or earthquake, but by an invisible tempest originating from the heart of the sun. In 2025, as the sun nears the peak of its solar cycle, the threat of a powerful solar storm looms large. Such an event, when it strikes Earth, would ripple across every continent and sector of society, exposing vulnerabilities in a world more connected and dependent on technology than ever before. The impact would be both immediate and far-reaching, affecting everything from basic utilities to global economics, security, and daily life. At the center of the disruption lies the electrical power grid, the backbone of modern civilization. Transformers overloaded by geomagnetically induced currents could fail catastrophically, causing widespread blackouts. Unlike many natural disasters, power grid failures caused by solar storms can span entire countries or regions simultaneously, with repair times stretching into months or years. Transformer manufacturing is specialized and time-consuming, with replacement parts not readily available in large quantities. This prolonged outage would cascade into other critical systems. Water supply, sanitation, heating and cooling, traffic control, and emergency services depend on electricity. Hospitals might struggle to operate life-saving equipment without backup power. Refrigerated medicines could spoil. Communication networks could degrade, hampering coordination. Transportation systems would be severely affected. Air traffic relies heavily on satellite navigation and communications, both vulnerable to solar storm disturbances. Ships and trucks, depending on GPS for routing, would face navigational challenges, delaying deliveries of essential goods. Fuel supply chains, relying on pumps and electronic monitoring, could falter. Urban mass transit systems, traffic signals, and rail networks could experience failures, compounding the chaos in densely populated areas. Communication networks would face unprecedented strain. Satellites used for television broadcasts, internet connectivity, and phone services could malfunction or be temporarily disabled. Ground-based fiber optic and wireless networks might experience overloads or disruptions due to power outages and electromagnetic interference. Without reliable communications, emergency response efforts would be hampered, public information campaigns delayed, and social unrest could rise as uncertainty and fear spread. The global economy, tightly interwoven and reliant on digital infrastructure, would encounter serious setbacks. Financial markets, banks, and payment systems that process trillions daily could freeze or operate unreliably, triggering panic and economic instability. Supply chains for food, medicine, and consumer goods, already delicate in many sectors, would suffer delays and shortages. The ripple effect would impact everything from manufacturing to retail, from agriculture to healthcare, threatening livelihoods and national stability. National security concerns would heighten dramatically. Military operations depend on satellites for reconnaissance, communications, and missile warning systems, all vulnerable to space weather. The inability to maintain secure communication or navigation could compromise defense readiness. Coordination among allies during a crisis might falter, increasing risks in tense geopolitical situations. Cybersecurity risk could multiply as power outages and system instabilities create openings for malicious actors. Despite these daunting scenarios, the story of a solar storm hitting Earth in 2025 is also one of hope, a testament to human resilience and the advances made in preparedness and mitigation. Recognizing the threat posed by space weather, governments, space agencies, and industries worldwide have invested heavily in monitoring, forecasting, and hardening critical infrastructure. Space weather observatories now provide early warning systems that can detect solar flares and CMEs hours or even days before impact. This lead time allows satellite operators to power down sensitive instruments, power grid operators to adjust loads and protect transformers, and airlines to reroute flights. Real-time data sharing among international space weather centers has improved the accuracy and timeliness of warnings, enabling coordinated global response. On the ground, power utilities have begun installing devices designed to block or divert geomagnetically induced currents, reducing stress on transformers. Advances in transformer design make new equipment more resistant to damage. Smart grid technologies help isolate affected areas and reroute power to minimize outages. Emergency planning exercises simulate solar storm scenarios, improving readiness among first responders, utilities, and governments. Public awareness campaigns have grown, educating people about solar storm risks and encouraging preparations similar to those for other disasters. Emergency kits, alternative communication plans, and backup power solutions. International collaboration fosters research and policy coordination, recognizing that space weather is a shared global hazard. Looking forward, scientists continue to deepen their understanding of the Sun-Earth connection. Missions like NASA's Parker Solar Probe and ESA's Solar Orbiter venture closer to the Sun than ever before, gathering unprecedented data about the origins of solar storms. This knowledge is critical for improving forecasting models and developing technologies to better shield satellites and terrestrial systems. The looming solar maximum of 2025 is a reminder that Earth exists within a dynamic and sometimes hostile solar environment. It is a call to action, to strengthen resilience, to foster international cooperation, and to build a society capable of withstanding the sun's most powerful outbursts. The impact of a solar storm is not limited to technology. It is a profound challenge to how humanity adapts to its cosmic neighborhood. Ultimately, the narrative of a solar storm hitting Earth is one of balance, between the overwhelming forces of a star's tempest and the ingenuity of a civilization striving to understand, prepare for, and mitigate natural threats. As the sun's activity waxes and wanes, so too does our vigilance and readiness. The story is ongoing, a cosmic drama with Earth's fate tied to the rhythms of the sun, urging us to look upward with respect and preparedness as 2025 approaches.